Hi everyone, and welcome to this video. Today, we'll be exploring how to perform multi-body dynamics and motion analysis in Altair Inspire using a rack and pinion mechanism as our example. In this video, we'll go through the entire workflow to simulating motion. Let's dive right in. First, we begin by importing all the necessary parts into Altair Inspire. These parts include the rack, the pinion gear, the shaft for the pinion, and the handles required to rotate the shaft. Altair Inspire allows us to easily import these parts in different file formats like STEP, IGS, or STL, depending on your design needs. Once the parts are loaded into the software, we organize them into two rigid groups. The first rigid group consists of the pinion gear and its shaft, as these will rotate together as a single unit. The second rigid group consists of the handles, which are the components that will drive the motion of the shaft. Grouping the parts into rigid bodies simplifies the analysis process by treating the components as one unit, thus reducing unnecessary degrees of freedom in the simulation. After organizing and grouping the parts, it's time to position them correctly in the 3D workspace. First, we move the rack into its final position on the grounded part. The grounded part acts as the reference for the entire mechanism, essentially serving as the base of the system. By positioning the rack correctly, we ensure that the subsequent motion simulation behaves as expected, with the rack properly interacting with the pinion gear. Proper alignment here is key to making sure the rack moves in a straight line when the pinion rotates. Next, we begin the assembly process by positioning the pinion gear next to the rack. After the pinion is aligned with the rack, we move on to attach the handles to the pinion shaft. These handles are the components that will be used to turn the pinion, thus driving the motion of the rack. Once all the components are positioned correctly and aligned, we have a fully assembled model, ready for joint creation. With the assembly complete, the next step is to establish the interactions between the parts. In Altair Inspire, joints are created using the Joints menu, but the software streamlines the process by automatically recognizing the joints present in the model based on the assembly's geometry. This automation saves time and ensures accuracy, as the recognized joints align with the intended mechanical behavior of the system. Once the joints are established, we proceed to define the key contacts. The first contact is between the rack and the grounded part, ensuring the rack remains constrained to its sliding path. The second is between the rack and the pinion, where the gear teeth mesh to transfer motion. Using the Contact Definition tool, we select the interacting surfaces and the software calculates the behavior based on their geometry, ensuring precise motion simulation. These steps establish a robust foundation for analyzing the system's movement in the next phase. With the joints and contacts defined, the next step is to add motion to the system by incorporating a motor. Using the motor tool in Altair Inspire, we assign it to the revolute joint of the pinion shaft. By default, the motor applies constant rotational motion, but we can customize its behavior by modifying the input graph. For instance, changing it to a sinusoidal waveform allows us to simulate oscillating motion, where the pinion rotates back and forth. This setup replicates real-world motion and ensures the mechanism performs as intended. After configuring the motor, we run the motion simulation to visualize how rotational motion from the pinion translates into linear motion of the rack. Altair Inspire not only provides a clear animation of the mechanism in action, but also allows us to analyze key data like displacement, velocity, and acceleration. These insights help us evaluate the system's performance and identify any areas for improvement. In conclusion, the workflow in Altair Inspire, from assembling the model and defining interactions to adding motion and running simulations, offers an efficient and intuitive way to design and analyze mechanical systems. With this process, you can confidently test and refine your designs for optimal functionality. Thank you for watching the video.